So welcome to LNP Renewable System Integrator. Today we are going to discuss PID control systems in the BLCs. Okay, we are going to discuss some of the basics with some example. So if you are going to work in a building automation and control system environment, or if you are working as a BMS technician or building management system engineer, you need to know some basics regarding this PID, because in most of the industrial automation projects, in most of the heat ventilation air conditioning systems, where we need to be precisely control the temperature and the pressure. So we need to know some of the basics. So today, what are the things we are going to discuss? What is a PID control loop, where it is used, and how a manual PID loop is being observed. Okay, how we can calibrate the auto control. Okay, and also today we are going to discuss how to configure a PID wizard in a step 7 Siemens micro software, and also how to open the and configure the PID in a Delta ISP software. Okay, and also we are going to explain you with some simulation examples. So we are going to discuss 3 examples with the 3 different environmental settings today. So first, what is a PID loop? So it is generally designed, okay, to generate an output that has some corrective effort. Okay, so say for example, there might be some error values. So even in case of, say for example, if you want to open a damper actuator 100% or 80%, if the temperature is this much percent, but if the temperature and the pressure are not ideal things, these are changeable things. Okay, it often changes. Okay, based on the environment, based on the system settings. Okay, for sure there is a possibility for these physical parameters to change. They are variable parameters, they cannot be perfect at any time. So in order to configure that errors, okay, in order to clear that offset values and the errors, we are going for this PID control. Say for example, you had already programmed. Okay, if you are getting a fixed output, you can make it a program that if it is a 40-degree, my damper actuator has to open this much. If it is a 25-degree, it has to close this much. Like this, if you're trying to tend to make any sort of programs, okay, only for the fixed things it will work. But when you're going for temperature or a pressure control, in such places, you cannot expect the perfect output from that sensors. So if you're receiving some input, okay, and you need to balance it, okay, in order to make a corrective effort to get that to make that function to work properly. Say for example, you're getting a 35-degree temperature, okay, or if you're getting a 38-degree temperature, okay, as you had already programmed that for a 40-degree temperature the damper has to open fully 100%. Okay, so the 38-degree temperature is maintained for a long time, so it will create there is a possibility for it to create a temperature. In such places, in order to adjust that 2-degree, okay, in order to adjust that 2-degree, with the help of this PID loop, we can establish that one. So if you want to create a controlled environment for a heat ventilation air conditioning system, there you normally go for this PID control loop. Okay, if you're going for a everyday control, simple example we can tell. If you're going for a riding a car in a hill station, okay, so if you're ascending a hill, okay, maybe if you lower speed, there is a possibility for the vehicle to come back. So in such occasions, for the cruise control, okay, we can use this PID loop. So we can make an algorithm and restore it. So what the algorithm will do, it will get the output, okay, and also it will get the input. So it will compare them, it will process it, and it will try to restore the set speed which is required to run or to climb this hill with the car. Okay, to move your car in ascending direction in the hill. Say for example, you're driving a car, okay, in a hill you need to run at a speed of 70 km/h, then only it is climbing that hill. Okay, sometimes if PID or if cruise control is not activated, say for example I'm telling, if the cruise control is not activated by default, what will happen? You might be going in a 50-degree, the vehicle will throttle. It may face a difficulty while ascending a hill. So if the cruise control is activated, Okay, so the PID algorithm is getting activated. So it will try to monitor the smooth control when happens. So when you run your vehicle at a 70 km speed, it is running smoothly over the hill. So it will note down that 70 might be the set point. We need to try to maintain the set point. So what will happen? So even when you try to give a accelerator at 50 degree also or 55 degree also, it will try to increase the speed to 70 so that the engine will run and you can move it smoothly. So it means that it will identify the process, the proportional and integral derivative when activated inside a car or cruise control. What will happen? It will identify, okay, 70 km/h speed is the perfect speed to be maintained. So what it will do, even if it is a 65 degree, it will try to produce the output to 70 km/h so that it will move smoothly. So this is the purpose of this PID control. Okay, and even okay, in building automation systems for the precise control of temperature and pressure, we can use it. See here, we can have a thermostat, so we can set a set point at 70 degree Fahrenheit. Okay, and at present your present value is 72 degree. So what it will do? So it will try to lower it to 70 degree. Okay, or say for example, this present value input you will get from the sensors. The sensor will produce the electrical output. Okay, with the help of this transmitter. In the same way, if your set point is 70 degree and the present value is only 68 degree, in order to maintain the 70 degree, what will happen? So you need to cool it more. So whatever the required operation is required, it will do it automatically with the help of this PID control. See, this is an industrial example. Okay, we are turning a motor on and off. Okay, when a particular level is reached inside a tank. So we are filling a tank. Say for example, our set point is 50 degree. If the 50% of the tank is full, then the water supply should stop. Then the motor should turn off. If it is lower than that, it should turn on. Like that, we are going to make an automatic control. It's a basic, simple example of a PID closed loop control. See here what is happening. So it is 40% is immediately reaching. If it is go beyond that also, it will reduce. So the controller will make a note that the filling of tank should not go beyond the set point, and it also should not go below the set point. It will try to maintain the set point. It will on and off automatically. So this is a basic simple example how a PID control loop is being established in the industries. See here now, now let us create a graphics and let us create a PID inside any sort of controllers you are having. Okay, you're trying to monitor it manually in order to identify the important critical points. Now, so what we are going to do in the manual operation, we are turning the motor on and off. Okay, we are turning the pump on and off. See what is happening. When it is on, it is rising. When it is off, again it is lowering. When it is on, it is again rising. Here we didn't give any set point value. We don't have any preset value. Only we are observing the output. How much maximum it can go when it turned on. That is the only thing we are observing in the manual flow loop. See here. Basically, this proportional integral derivative will be inside this controller. Okay, so what is its duty is it will observe the output. Your output may be 4 to 20 milliamps. Maybe we might have converted it to 0 to 100%, or if it is in memory bytes 0 to 32765, based on the memory level we used to create it. Okay, and the flow transmitter, we have the flow transmitter. From the flow transmitter, okay, you will try to calculate the flow. Oh, this is the flow which is happening. So that output also will take as a process variable. Okay, and this proportional integral derivative will compare the set point and the present value. If there is a much difference, in order to compensate that difference, it will produce the required essential output. This is how basically a proportional integral derivative loop will work inside any sort of PLC controllers. See here. So if you want to know what is the error point, simple. So you have a set point and you have a process variable or a present value. So set point minus the process value will gives you the error. Say for example, if your set point is 72 degrees Celsius, okay, or 72 Fahrenheit, and your present variable is just 70, okay. So if it is a flow, you can calculate in meter cube or in liters. So based on your needs, the unit that you're going to assign, you can calculate. Consider the value as set point as 72 and your process variable is 70, the error value is 2 degree. Okay, if you're calculating the gain into the error value, you will get the proportional output. Okay, and if you want to know the controller output, so you need to know your present controller output plus the gain into error value. Okay, and for the process variable and the set point, there is much differences. That in order to compensate that differences, the controller will work on. Now let us try to know if you are opening a step 7 micro software, okay, PLC software. Now you want to open a PID wizard, proportional integral derivative wizard. Before opening it, okay, if you open it, you need to configure the following things. First, you need to configure the number of loops that is required. It can be from 0 to 7. Okay, and next you need to assign a name for a loop. Okay, and you need to set the loop parameters, and you need to set the loop input and the outputs, that is the memories. And if there is any critical point that you want to raise, say for example, if the pressure is this much high, I need to raise an alarm, so then you can set the loop alarms also. Okay, and even in certain places, if you have any subroutines or if you have any interrupts, you can configure that as well. And most importantly, whatever you assign, whatever parameter you assign, whatever input you assign, whatever output you assign, for everything to get stored, you need a memory. For that, we need to allocate the memory, and at last we need to generate the PID project components. See here, this is how it looks like. So when you open a step 7 software for the PLC controller, so this is the PID wizard. So when you open it, you will get all these things. Okay, basically it will looks like this, and you need to assign everything, gain value. So these gain values, everything, after analyzing it in manual, we need to make it to automatic. You can assign each and everything, sample time, integral time, how much you required, everything you can assign. Next thing, as we told earlier, we need to assign the process value scalings. So what shall be the lower level and what shall be the higher level? What shall be my loop set points? So all the things you can set. And most importantly, you need to know the scalings, whether it's a unipolar or a bipolar. So what is the maximum memory bits that you have? 0 to 27648. Okay, and what type of input that you're going to get? That is an analog input. Okay, and next we need to allocate the alarms. So you need to save the alarms in a particular location. For that, you are using a memory VB120. In the same concept, okay, if you open a PID control block in a Delta ISP software, okay, you can enable any sort of functional block and change the name to PID. You will have a 4 parameters to use. One is S1, S2, S3 and D. For all these, you need to assign a memory. Okay, D0, D1, D100, D150. It's up to your requirement. Okay. So what is S1? S1 here refers to the set point value. And what is the S2 inside this PID? That is present value. And what is S3? S3 is nothing but the parameter setting that you're going to make, and D will be your output value. Okay, so as we told earlier, the Delta ISP software, you're going to assign the PID. For that PID, you have a S1, S2, S3 and the D. S1 will be the set point, S2 will be the present value, and S3 will be the parameter settings. It might be for a 16 bits, it uses 20 consecutive devices. For 32, it will increase. Maybe it might be 40. Okay. So now let us try to know with an example. So here consider an environment where, as we discussed earlier, we analyzed a pump, okay, by making it manually on and off. Now we are going to switch off the pump. Okay, and just what we are going to do, we are going to change the controller to auto operation. Okay, we will set the gain as 1. Okay, and our set point value was 0 initially, so we are changing it to 10%. See what will happen when the pump is off. What is happening? See here, what is the output it's trying to produce? So it will try to produce its output to 50%. So you can see here what is happening. So it is in the output was in the 50%. So the controller making it to 60% because we are assigned our set point to 10%. So 10% increase, we are going to make in the output. So this is how basically when there is no preset value, you're assigning only the set point and the gain. So this is how the output will work. This is a simple example. Now let us try to know the example in detail. So as we know earlier, if you want to know the controller output plus gain into error. So as we know earlier, what is the gain that we assigned? Our gain is 1. Okay, and what is the as we know earlier, our gain is 1. And what is the error? We already know. What is the error? Set point minus PV. So set point is 10 and the present value is 0. So what will be our difference? It will be 10. So 10 into 1, it will be 10 only. So already we know our controller output. Our controller output was previously 50%. Okay. Now our gain and gain along with the error was 10%. So 50 plus 10, we are getting an output of 60%. So this is how the controller is assigning its values, okay, based on the gain and the set point that we are assigning. See here also the same example only I am telling. So from 50%, it's changing the output to 60% because of the set point that we assigned and the gain that we assigned. Okay. Next, let us try to know the other example. Here, what we are going to do. Here, most of the conditions are going to be the same. Okay. Here we are not. Here also we are not going to make the motor on. Okay. Only thing that we are doing is that we are changing the set point to 20%. Okay, and we are changing the gain value to 2. Okay, and we are making the controller in auto operation. Now let us observe what sort of output change is happening. See here. So it is in the from the 50%, it is raising to 70%. Why? Because we know earlier our set point is 20%. So in order to achieve that set point, we also assigned a gain to 2. So to produce the required concerned output based on this gain and set point, now it is 70%. It is changing from 50 to 70%. Here in the same calculation, as we know earlier, for a controller output plus error into gain value. This is the formula. So we know our previous output is 50%. Okay, and what we are going to do? So what will be the error value? Set point minus present value, or set point is 20% and the present value is 0. So our error is 20, and what is the gain? It is 2%. So what is happening? 2 into 20, what will happen? It is a 40%. So 40 plus 50, what will happen? 40%. Correct? So 40% plus 30, what will happen? The output will be 70%. See here, this is a simple example. Now, most importantly, in the example 1 and 2, we never turned on the pump. Okay, so whatever set point that we fix and whatever gain that we fix, when we turned our controller to auto, it is obeying perfectly because there is no present value. Make sure, okay, there is no present value. The present value was 0 because our pumps are off in both the condition, in example 1 and 2. So that's why we are getting a static and perfect output. Okay, now in the present value, okay, you can give any sort of value. Say for example, based on the temperature, you need to control the damper actuators, or based on the pressure flow value, you need to control the speed of the pump. Okay, so like this, based on the flow value or a present value, you need to control the valves which we are operating in the pipelines. So whatever you want, you can provide that concerned output in the ranges, that is from along with the set point ranges. Okay, so now let us try to enter this with an other example. So we already know it. So we had observed in the example 1 and 2, we had observed the pump operation with the help of the PID in a static conditions, because we never turned on the pump, we just turned off our pump. In the first, we just turn on and off and we analyze how much maximum output it can produce, and in the second operation, So we had we had assigned the set point and also we had assigned the gain. So gain in the first example we had assigned the gain as a 1 and set point as a 10%. In the second example we had assigned the gain into 2, gain as a 2 and set point as a 20%. We never turned on the motor. Now we are going to analyze it in the dynamic changing environment. So in the third example, what we are going to do, we are going to turn on the pump, okay, and we are going to assign the set point value to 75%, or sometimes we can change it to 65%, because we already know when we turned on a motor manually, it is going up to 80%. So now what we are going to do, we are going to assign the set point to 65%. Okay, here we are going to assign the gain as a 2. Okay, so what will happen here, the conditions, what is the condition? Pump will be on. Okay, our gain value is 2%, 2, and the set point we are assigning is from 75% is maximum value, but what we are going to do, we are going to assign it to 65%. Okay, see here what is happening. Even though, okay, when the pump was on, it is trying to change the environment. Okay, the output is trying to go up to 75, but because of this set point, what is happening, it is trying to pull back that output from 75 to 69%. So this is how basically, it is trying to control its output, because we had already set a set point that I need only the 65% output of this motor. Okay, I'm giving you the gain of 2%. So what the controller is making a calculation. So as we know earlier, okay, so output will be produced based on that formula in a PID. That is, our output will, say for example, consider our output value as a 75% plus, okay, our 65% is our set point, okay, and our present value was 75%. So if you want to calculate the error between these two, set point minus present value, what will be 65 minus 75, what will happen? We'll have a 10% change. What is happening? We have a 10% error. Okay, 10 is the error value. What is the gain already that we are having? Our gain value is 2. So 10 into 2, it will be 20. So what is the output that we are getting? So as we know earlier, so maximum up to 69% only the output will go. This is how normal PID will enable. Okay, it will control the output based on the set point and the gain values. You get understood now? Our set point is 75, process value 75%. So we are making the set point to 65%. No, I don't need 75% output. I need to control it in 65%, like that. You're providing a set point. Okay. So what is happening? And you also you're providing a gain value as a 2. So initially, when the pump was start, it will try to go to 75%. But because of this set point, what the controller is doing, it is trying to bring it down to 69%, trying to make it under his control. And also most important thing that we know, we should know inside this is the offset value also we need to know, because when the present value and the set point value are not equal, okay, the difference between the present value and the set point, present value is nothing but the process value, that is the set point. Your error is going to be a set point inside the controllers. Thank you so much. Please subscribe and press the bell icon. If you want to know more and learn more, you can contact us. We have provided the contact details in it. We are providing design, installation, testing and commissioning support for industrial automation, home automation, building automation, and for the PLCs. And we are also providing design, installation, testing and commissioning support for solar on-grid, off-grid and hybrid applications. If you want to know the electric vehicle basics also, you can contact us. We have provided the contact details in it. And most importantly, as we know earlier, even inside the software also I will show you how it will work, because I had already provided the screenshot, and also we are providing a simulated output also, how basically the manual operation is happening, how basically the PID loop is working. Okay, when the gain in the set point is changed from one value to other value, and at the static condition what is the output, and at the dynamic condition how the output is getting changed, and what is the offset, all these things we have discussed. So if you have any queries, if you want to know regarding this, you can contact us on chargeable basis. We are providing trainings to the colleges and the technical institutions. We are ready to conduct the workshops also, so we had provided the contact details in it. Thank you so much. So this is the ISP software. As I told earlier, this is how the PID, and these are the values that we assigned in it. Okay, normally if you select this block, the PID block, it will come. Whatever name, this is nothing but a normally API block selection. This is a functional block. So in the functional block, if you name it as a PID, or immediately everything will come like this, and you need to assign the memory, required memories for it. Okay. See here, so as I told earlier, S1 will be the set point, and S2 will be the present value, and S3 will be the parameter settings. Okay, and D will be the output. So same way inside this PLCs also, inside the tools, see here, this is the PID wizard. After selecting this wizard, whatever things that we share in the screenshot, you will have, you need to assign them one by one, so that you will try to know how a PID will work. Okay, basically. Thank you so much.